Okay, so to finish the section up, we're going to get one more theorem, and then we're going to apply a couple examples, and that should do it. So, so we're going to get this theorem called the first derivative test. So this is first derivative test for critical points. Again, remember critical points, those are points where the first derivative is either 0 or is undefined. So for this theorem, we're going to assume that f of x is differentiable and we're going to let c be a critical point of f of x. Then the following two things happen. If we get f prime of x changes from positive to negative at c, this implies f of c is a local max. And we get if f prime of x changes from negative to positive at c, that will imply f of c is a local min. And remember, like I said earlier, the AP test, they use relative min and relative max instead of local min and local max sometimes. So they'll kind of refer to these in either way. So just to kind of illustrate, and so we kind of see what's going on here. If we had, say, a function like this, the first derivative of the function is the slope of the tangent line. So the first derivative is 0 here, and the first derivative is 0 there, which would mean that these 2 points are critical points. We can see if the slope of the tangent lines here are positive, and then those positive slopes of tangent lines change to negative across this point here. That's why we create a local max. If the first derivative changes from positive, then it's 0, then it's negative, that'll be local max. And if you get the first derivative is negative, then it's 0, then it changes over to positive, so negative to positive, that'll create a relative min. So what we're going to look at here to finish up is a couple last examples, and then we'll be done with section 4.3. So this is example 4. And what this has to do is analyze the critical points. So analyze critical points of the function f of x equals x cubed minus 27x minus 20. So they haven't really said what to do with that. We're just going to try to tell, are the critical points relative max or mins, or we could say local max or mins. So anyway, we need the first derivative because we're going to be looking for changes in sign of the first derivative, either positive to negative or negative to positive across the critical points. So we need to get the first derivative and use that first derivative to find our critical points. So here's our first derivative. This is a parabola, so it's never undefined. So to get the critical points, we're just going to set that first derivative equal to 0. We don't need to set it equal to undefined. due to the fact that this thing's a parabola, so it won't be undefined anywhere. Okay, so we get 27 is 3x squared. Divide the 3, we get 9 is x squared. Plus minus square root of 9 is plus minus 3. So these are my x's. So when I go to build my table of values, we got negative 3, we got positive 3. F prime is out here. We got negative infinity up to negative 3, negative 3 to 3, and 3 to infinity. We're 0. First derivative is 0 at these points. So we need to figure out what's going on when we use a number outside of this. So let's say I get negative 5. Negative 5 squared is 25. 25 times 3 is 75. 75 minus 27 says the first derivative is going to be positive for this region. If I use like 0 here, 0 squared 0, 3 times 0 is 0. 0 minus 27 is negative 27, so we're negative in here. If I use 5 again out here instead of negative 5, if I use positive 5, 5 squared is 25, times 3 is 75, take away 27, and we're back to positive. So we switch from positive, the first derivative switches from positive to negative across the critical point, negative 3. So positive to negative, that says f of negative 3 is a relative max, or we could say local max. And again, it's not good enough to just point at the chart for the AP test. We need to kind of say why. So we'll say f of negative 3 is a relative max as it is a critical point. And f prime changes from positive to negative across it. Or say it's changed from positive to negative at x equals negative 3. So I'm just kind of quoting the theorem. We change from it's a critical point. We change from positive to negative at the value. So that says relative max, or you could use you could say local max. Local max and relative max mean the same thing. The AP test will use them interchangeably. Then for f of 3, we say f of 3 is a relative min as it is a critical point. And f prime changes from negative to positive at x equals 3. Okay. So we analyze the critical points. The first one's relative max because we have positive slope, then we have critical point, then we have negative slope, makes a relative max. Second one's a relative min because we have negative slopes of tangent lines, then the tangent line slope is 0, then it goes back to positive. So we end up with, So we end up with what we want there. Okay, so the next example, and then we just got one or two after that to wrap up the section. So this will be example 5. So we want to analyze critical points. And where the function is increasing or decreasing of the function equals cosine squared plus sine of x on 0 up to pi. Okay, so First, we need the derivative. Chain rule applies on the cosine squared of x. That'll be 2. Leave the cosine of x alone. 2 minus 1 is 1, so I'm not going to write the power. Then the derivative of cosine is negative sine. So we multiply by the inner derivative. Plus derivative of sine's cosine. These both have a cosine in it, so I'm going to factor the cosine out. And we'll get negative 2 sine of x plus 1 times cosine of x. This is my f prime of x. Okay, this is just some sines multiplied together, add in some stuff, and then times a cosine. It's not going to go undefined anywhere, so we're just going to check for our critical points. We're going to check where is the first derivative equal to 0. So I got two things that multiply together to equal 0. So it's got to be the case either the first thing equals 0. So negative 2 times sine of x plus 1 is 0. Or the second thing, 0 equals cosine of x. Let's move the 2 sine of x term across so it becomes positive. Divide the 2. So we're looking for where is sine of x equal to a half. So if we think about the unit circle, we're asking where is sine, which is the y value, where is that a half? That should happen at 2 points. It's going to be pi over 6 and 5 pi over 6. And then we say, okay, where on 0 from 0 up to pi is cosine of x 0? And that's going to occur at x equals pi over 2. That's when the x value is 0. The other point, cosine 0, is way down here, but that's outside of the 0 to pi range, so we don't use it. So we're going to break our real number line up into following parts. We're going to have 0 up to pi over 6. Then we're going to get the value pi over 6 itself. We have pi over 6 up to pi over 2. Make it pi over 2. Pi over 2 up to 5 pi over 6. 5 pi over 6. And then 5 pi over 6 up to pi. So these are the x's. We're going to build our table of values, and we're going to look at the first derivative. So this is 0, this is 0, this is 0. Okay, if I use my calculator for this, because this is going to be a little messy. Just want to, basically I'm going to put my first equation that I have there in the calculator, and then I'm going to set the independent variable to ask so I can type in different values and then see what we're going to end up with. Okay, so I need something between 0 and pi over 6. So I'm going to use like pi over 10. And that gives me a positive value back. So we're going to say we start out as positive. I need something between pi over 6 and pi over 2, so I could use pi over 3. And we have switched over to negative. I need something between pi over 2 and 5 pi over 6. I could do, I guess, 4 pi over 6. And we're back to positive. And then I need something 6 pi over 6 would be pi. I got 5 pi over 6. Here's 6 pi over 6. I'll do 5.5 pi over 6. That would be in between the two. And let me see. That'll give me a negative number back. Okay, so here are my intervals, assuming I've typed everything in correctly. These are my signs of f prime. So let's list the local max and mins first. If we go positive to negative, so sign change from positive to negative, that creates a local max. So we have, we'll say f of x has local maxes at x equals pi over 6 and x equals 5 pi over 6, as they are critical points. Again, on the AP test, you can't just put the chart and say, so this happens, you have to say why. So we say they are critical points. And I guess we say of what? Critical points of f. And f prime changes from positive to negative at them. All right, so we got the local maxes taken care of. Let's look at local mins next. So local min will be a sign change from negative to positive across a critical point, which happens at pi over 2. So we'll say f of x has local min at x equals pi over 2, as it is a critical point of f and f prime changes from negative to positive. At it, I guess we could say. Okay, so we analyzed the critical points. Now we need to say where is the function increasing or decreasing. And if you remember, we had that other theorem we did in the previous section, which says if the first derivative is positive, then the function that you took the derivative of is increasing. And if the first derivative is negative, then the function you took the derivative of is decreasing. So we'll say f of x is increasing on 0 up to pi over 6 and pi over 2 up to 5 pi over 6, as f prime of x is greater than 0 and f of x is decreasing on pi over 6 up to pi over 2 and 5 pi over 6 up to pi, as f prime of x is less than 0 there. So we're increasing where the first derivative is positive, regions where the first derivative is positive, and we're decreasing on regions where the first derivative is negative. So we got our table, got our chart for our first derivative, and then we were able to go through from that and tell our local max and mins, and tell where the function was increasing and decreasing. Okay, final one here from the section. This will wrap up 4.3. We want to analyze the critical points of a function f of x equals 1/3 x cubed minus x squared plus x. Okay, so what we're going to do, since it's asking us to analyze the critical points, in our book that means figure out if they're local max or mins or if they're something else. So we're going to look at the first derivative so we can figure out the critical points. We get 1/3 times 3x squared minus 2x plus 1 which is, that can cancel. X squared minus 2x plus 1, which is x minus 1 times x minus 1, which is x minus 1 squared. So we can kind of look at this. X minus 1 squared, that's parabola. It's never undefined. It's 0 when x is 1. So we'll say we have a critical point at x equals 1. It makes the first derivative 0, and just since this is kind of a simple function, rather than setting this equal to 0 and algebraically solving it like we did in some of the other problems down here, we're able to kind of look at this form and just tell that x equals 1 will make the first derivative 0. So we're going to build up our table for it. We have 1 here. We got negative infinity up to 1 on this side. And we have 1 up to infinity, and 1 makes the first derivative 0. Okay, so let's grab a number from over here and kind of think about it. If I use 0, if I put 0 in for the function, 0 minus 1 is negative 1, but that gets squared. When you square a negative, it's positive. And if I put a number bigger than 1, like 2 or 3, 2 minus 1 is 1. When you square it, it's positive. So we have a critical point. We're positive on one side and we're positive on the other. So what this says is f of 1, so that's the y value of our critical point, is neither a local max or local min, as f prime does not change sign. Oops. Spell things correctly. Not change sign across x equals 1. So there is no change in sign at x equals 1, which means the y value is neither a local min or a local max, because you didn't get a change in sign of the first derivative. 1 is a critical point, but there's no change in sign. So when there's no change in sign at a critical point, it does not create a local max or a local min.